section 13.1, we begin the topic of chemical equilibria. In chapter 12, we were studying. In section 13.1, we begin the study of what is known as chemical equilibria. In chapter 12, we were studying chemical kinetics, which describes how fast a product is produced. So whenever you are presented with a problem that is discussing the speed of a reaction, then that's going to be a kinetics problem, and we're going to be doing things like integrated rate laws and method of initial rates in order to solve that problem. Chemical equilibrium properties describe how much product can be produced. That is, if we want to know how much product is made, we're probably going to be doing an equilibrium type calculation. Now, previously, when we were interested in how much product was being made in a chemical reaction, we would use stoichiometry. That is, we would do calculations involving mole ratios and moles in order to determine the amount of products that were being produced. So, for example, if I had this reaction here where 1 mole of A is being converted into 1 mole of B, I would understand that the moles of A reacted equal the moles of B produced because the mole ratio between these two things is 1 to 1. Now, when we were doing these simple stoichiometry calculations in the past, we were assuming that the reverse reaction is not occurring at all. As we saw in chapter 12 when we were discussing reaction mechanisms, sometimes the reverse reaction is significant. For example, if we have a reaction mechanism where the first step is fast and the second step is slow, then what will happen is the products from the first step will build up, and that will cause an increase in the rate of the reverse reaction for step 1 here. Eventually, we'll obtain a scenario where the forward and reverse reaction for step 1 are occurring at equal rates. And we saw this when we were talking about figuring out rate laws for a mechanism where the first step is fast and then one of the subsequent steps is slow. So a system like this, where the forward and the reverse reactions are occurring at the same rate, is described as being at chemical equilibrium. So imagine this reaction, A plus B gives C, and what's going to happen is initially we'll have a high concentration of A and B, so the forward rate will be quite fast. At the beginning of the reaction, when there is no C, the reverse rate will be slow. But as the reaction progresses, A and B get used up, therefore the rate of the forward reaction decreases, but C gets produced and increases in concentration, so the reverse rate increases. Eventually you reach a point where the forward rate equals the reverse rate, and we say that equilibrium has been achieved. So a system where the forward and the reverse reaction are occurring at the same rate is described as being at equilibrium. An important quality of systems that are at equilibrium is that the amount of products and reactants remain constant. There are a couple of analogies that you can use to think about this. One example is imagining a car park that is completely full. Even though it is completely full, because the rate of cars entering equals the rate of cars leaving, something is always happening. Cars are always entering, cars are always leaving, but the number of cars that are in the car park doesn't change. So that's a good example. Another example that's more chemistry related is the example of vapor pressure. So imagine a liquid. We're going to put it into a container up to this little mark here, and then we're going to put a stopper in there. And what will happen is that some liquid particles will leave the liquid and enter the gas phase, and the pressure above the liquid will build up. Because liquid particles are leaving the liquid, the volume of the liquid will go down. Because the liquid particles are entering the gas phase, the pressure above the liquid will increase. Eventually, you'll reach a scenario where the rate at which particles are returning from the gas phase into the liquid equals the rate at which they are leaving the liquid and entering the gas phase. At that point, the pressure up there stops changing, and the volume of the liquid down here also stops changing. And we say that the liquid is in equilibrium with its vapor. In fact, this is what we call the vapor pressure. The vapor pressure of a liquid is the partial pressure of a liquid when it is in equilibrium with its vapor. So that concludes the section on chemical equilibria.